Imagine a day that never ends and a night that never comes. The Earth's spin makes our clocks tick and our shadows move. The planet turns once around its axis in roughly 24 hours. That number is not a coincidence. It is the result of how the solar system formed. In the swirling cloud of gas and dust that collapsed to make the sun, tiny clumps began to spin. As those clumps gathered mass, the law of conservation of angular momentum forced them to spin faster, much like a skater pulling in her arms. The Earth inherited that spin and has kept it for 4.5 billion years. When we say the Earth rotates, we are describing a steady motion that is easy to miss because it is constant. You cannot feel the spin directly, but you can feel its indirect effects. A simple way to notice is to compare weight at different latitudes. At the equator, the outward pull of rotation, what physicists call centrifugal force, cancels a tiny fraction of gravity. A person weighing 70 kg at the pole would weigh about 0.5 kg less at the equator. That difference is small, but it is measurable with a precise scale. Centrifugal force also reshapes the planet. The steady spin pushes material outward, making the equator bulge. The Earth is not a perfect sphere. It is an oblate spheroid, about 21 kilometers wider at the equator than at the poles. That bulge is a permanent record of the planet's rotation. I find it hard to picture a perfectly round Earth because the bulge is built into every map and satellite image. The daily spin creates the familiar day-night cycle. As the planet turns, any given spot moves from the sun's glare into its shadow and back again. The cycle is regular enough that ancient peoples could count the passing of time by watching the sun rise and set. Modern clocks still rely on that rhythm, even though we now measure seconds with atomic vibrations. The cycle also governs the temperature swing between sunlit and dark sides, a swing that drives winds and ocean currents. Those secondary effects belong to later chapters, but the basic alternation of light and dark is rooted in the spin alone. Angular momentum is a quantity that remains constant unless an external torque acts on the system. For a rotating sphere, the momentum depends on its mass, shape, and spin rate. Because space is essentially empty, there is nothing to apply a steady torque to the Earth, so its spin persists. Tiny torques do exist, tidal friction from the Moon, for example, but they change the rotation only by a few milliseconds per century. That slow drift is why the length of a day is not exactly 24 hours, but a little longer when measured against distant stars. The origin of planetary spin is not uniform across the solar system. Some planets spin in the opposite direction to most, and some rotate far faster than Earth. Those differences stem from collisions and gravitational nudges during the early chaotic era of planet formation. Earth's relatively moderate spin is the result of a balance between the initial angular momentum of the protoplanetary disk and the random impacts that later reshaped it. We don't really know the exact sequence of events. The evidence is a patchwork of crater counts, orbital dynamics, and computer models. If the Earth were to stop rotating, the consequences would cascade through every system that depends on the day-night rhythm. But even before such a hypothetical, the present spin already defines the planet's equilibrium. The equatorial bulge, for instance, influences how the oceans sit on the surface. The slight reduction in effective gravity at the equator means that water is a little thicker there, contributing to the shape of the seas. The bulge also affects satellite orbits, which must be calculated with the Earth's flattened shape in mind. The spin also determines how we experience the heavens. Stars appear to move across the sky because of Earth's rotation, completing a full circle each night. The rate of that apparent motion is exactly 1 revolution per sidereal day, about 4 minutes shorter than the solar day we use for calendars. Astronomers use that precise rate to point telescopes and to predict when a particular star will be visible. The constancy of the rotation provides a reliable backdrop for all of those calculations. One might wonder why the rotation period is close to 24 hours instead of some other number. The answer lies partly in chance and partly in the physics of the early solar system. The original angular momentum of the Earth-Moon system set a baseline, and subsequent tidal interactions have lengthened the day ever so slightly. Over billions of years, the day will continue to lengthen, but the change is imperceptible on human timescales. It is a reminder that the spin we take for granted is not immutable, just very slow to change. The concept of conservation of angular momentum also explains why a figure skater spins faster when pulling in her arms. The Earth cannot pull its mass inward the way a skater can, but the principle is identical. If the distribution of mass changes, the spin rate adjusts to keep the momentum constant. In Earth's case, the mass distribution is set by the solid mantle, the fluid outer core, and the oceans. Small shifts, like the movement of tectonic plates, can alter the moment of inertia ever so slightly, leading to minuscule adjustments in rotation speed. Those adjustments are measured by very sensitive instruments that track the length of day. Even the feeling of standing still on the surface is a subtle illusion. The ground beneath your feet is moving at roughly 1,000 kilometers per hour at the equator, yet you do not notice because you share that motion with everything around you. The atmosphere moves with the surface, and the oceans flow in concert. The only way to break that illusion is to look outward, to the stars, or to launch a spacecraft that can see the planet's rotation from above. The day-night cycle also imposes a regular pattern on biological rhythms. Many organisms have internal clocks that sync with the light-dark rhythm. Those clocks, called circadian rhythms, adjust hormone release, sleep cycles, and even cell division. The spin, therefore, is not just a mechanical fact. It is woven into the fabric of life on Earth. While we will explore those biological links later, the mechanical foundation is the rotation itself. In the lab, measuring Earth's rotation is straightforward if you have the right tools. A simple pendulum, known as a Foucault pendulum, demonstrates the rotation by slowly turning its swing plane over the course of a day. The rate of that turn depends on latitude, confirming the link between rotation and position on the globe. Such experiments remind us that the spin is a physical reality, not an abstract idea. When we consider the origin of the spin, we return to the early solar nebula. Conservation of angular momentum forced the collapsing cloud to flatten into a disk, with most of the material spiraling inward to form the sun. The leftover material in the disk coalesced into planets, each inheriting a portion of the original spin. Collisions between planetesimals added or subtracted angular momentum, leading to the diverse rotation rates we observe today. Earth's spin is a snapshot of that ancient dance, preserved in the steady beat of a 24-hour cycle. A final point to note is that the spin also defines the direction of the Coriolis effect, which nudges moving air and water to the right in the northern hemisphere and to the left in the southern hemisphere. That deflection shapes weather patterns and ocean currents. While the full implications of the Coriolis effect belong to later discussion, the fact that it exists at all rests on the Earth's rotation. The quiet, relentless spin is a cornerstone of how the planet balances itself. It holds the shape, sets the rhythm of light, and keeps the angular momentum budget steady. If you stand at the equator and watch a weight on a scale, you can feel the minuscule lift that the spin provides. A tiny, steady reminder that the world beneath your feet is turning even as you stand still. The Earth spins at roughly 1,000 miles per hour at the equator. Imagine that motion snapping to zero in a single heartbeat. In a laboratory, we would call that an instantaneous deceleration, a step function in angular velocity that never occurs in reality. Yet the thought experiment forces us to confront the raw physics. The first thing to notice is that nothing attached to the solid crust stops instantly. The atmosphere, a massive envelope of gas, retains its eastward momentum. Its inertia means winds would surge eastward at hundreds of meters per second, turning the calm sky into a ferocious wall of air. I find it hard to picture a breeze turning into a gale that tears roofs from houses in a fraction of a second, but the numbers leave little doubt. The oceans behave similarly, though their density makes the effect slower to manifest. Water that has been circling the globe for billions of years would continue sliding across the seabed, generating tsunamis that dwarf any storm surge we have ever recorded. A single kilometer-high wave could race across a continental shelf before the water finally feels the drag of a now still floor. All that kinetic energy does not simply disappear. The rotational kinetic energy of the planet is on the order of 2.1 times 1029 joules, enough to power the sun for a few minutes. When the spin is halted, that energy must be transferred somewhere. In the atmosphere it becomes wind, in the oceans it becomes wave, and in the solid earth it becomes seismic shock. The release is akin to detonating billions of megaton bombs in the same instant, but the energy is spread through different media. The solid planet reacts with its own set of shockwaves. The mantle, a viscous rock layer, continues to rotate beneath a crust that is forced to stop. Friction at the mantle crust boundary would generate intense shear heating, perhaps melting the base of the lithosphere in localized zones. Simultaneously, the sudden change in angular momentum launches seismic waves that would race outward like ripples on a pond, except the pond is a sphere 8,000 km across. Those waves would be felt as a global tremor, a low-frequency rumble that could not be ignored. Because the crust is forced to decelerate instantly, the inertial forces on any structure anchored to it become extreme. Buildings, bridges, and even the ground itself would experience a sudden upward jolt as the planet's mass tries to keep moving. The pressure at the surface would momentarily spike, then drop as the atmosphere rushes eastward, creating a pressure wave that could shatter windows miles away. Friction between mantle and crust is not a smooth handshake. It is a grinding contact that would convert a fraction of the kinetic energy into heat. In regions where the mantle's flow is fastest, the heat could raise temperatures by several hundred degrees Celsius in seconds. That heating would be localized but enough to weaken rock, perhaps triggering landslides on steep slopes that are already destabilized by the shaking. The oceans, now moving relative to a stationary seafloor, would carve new channels in the sediment. The drag on the ocean bottom would be enormous, producing acoustic signatures that would dwarf any whale song. The sound of water grinding against rock would travel through the water column, reaching the surface as a low-frequency roar that could be heard for thousands of kilometers. All of these processes happen at once, overlapping in time and space. The atmosphere's eastward rush would collide with the still air near the poles, generating a massive shear zone that could spawn vortices the size of small countries. The resulting pressure gradients would be so steep that the usual balance between gravity and pressure would be thrown off, causing the air to compress and expand in ways we rarely see outside of explosions. Even the magnetic field would feel the shock. The liquid iron outer core, which generates the field through its own rotation, would suddenly find the mantle rotating beneath it at a different rate. The differential motion could induce transient currents, producing brief spikes in magnetic intensity. Those spikes would be short, but they remind us that the Earth's interior is not a passive backdrop. The immediate aftermath would be a planet screaming in every physical language we know: wind, water, rock, heat, and electromagnetism all shouting at once. The sheer scale of the event makes it difficult to imagine any single human experience that could capture it. It doesn't quite make sense when you say it aloud, because each component is so massive that our everyday intuition fails. One concrete detail that sticks in the mind is the behavior of a single ocean wave caught in the moment of halt. The crest, still moving eastward at about 200 km/h, would rise higher as the water beneath it slows, briefly forming a towering, almost vertical wall before gravity pulls it down. That fleeting, frozen crest, an instant where water defies its own weight, offers a small, observable glimpse of the chaos that would unfold. The Earth's spin stores kinetic energy in the oceans as a gentle, perpetual push toward the equator. When that push disappears, the water is left with a surplus of momentum that cannot simply vanish. In the first few minutes after the halt, the ocean surface would surge outward, seeking the new equilibrium of a sphere without a bulge. The surge would not be a slow tide. It would be a wall of water moving faster than a jet aircraft, a supersonic megatsunami that sweeps across continents in a heartbeat. I find it hard to picture a wave that fast, because our intuition is trained on wind-driven swells. The physics, however, is clear. The centrifugal force that once held the equatorial bulge at roughly 21 kilometers above the mean radius is gone. The planet's shape collapses by several hundred meters, and the sea floor follows. The ocean, still moving at roughly 460 meters per second at the equator, now has nowhere to go but downward and outward. In the first seconds, the water piles up along the former equator, forming a ridge that can be tens of meters high. The ridge is unstable. Gravity pulls it toward the poles, and the ridge collapses into a series of rolling fronts. Each front accelerates as it descends the slope of the collapsing bulge, gathering speed from the release of stored potential energy. The result is a cascade of megatsunamis that race toward the poles, each crest cresting at speeds that would shatter any coastal cliff in seconds. The flow toward the poles is not a gentle drainage. The water behaves like a viscous fluid forced through a narrowing funnel. As it converges, the velocity rises, pressure drops, and cavitation bubbles form in the deep ocean. When these bubbles collapse, they generate shock waves that travel through the water column, adding a rumbling hiss to the roar of the flood. The shock fronts would be detectable by seismometers as low-frequency tremors, a reminder that the ocean itself can shake the solid Earth. At the same time, the loss of the equatorial bulge lowers the sea level at low latitudes. Basins that once held shallow seas begin to drain, their floors exposed to air. The Sahara-type basins in the tropics would dry, leaving cracked salt flats where water once lapped. The Amazon basin, the Congo, and the Indonesian archipelago would all lose a substantial fraction of their volume. In the aftermath, the former river deltas would become barren plains, their sediments stripped away by the relentless surge. The water that reaches the poles does not simply pool in existing ice shelves. The polar regions, previously capped by thick ice, would be overwhelmed by a sudden influx of liquid. The ice, unable to accommodate the rapid rise, would fracture and float away as massive icebergs. The remaining water would spread across the polar caps, forming permanent seas that could be hundreds of meters deep. These new polar oceans would be fed by the continuous flow from the equator, creating a steady, albeit slow, circulation that replaces the vanished east-west currents. Because the Earth's rotation no longer supplies Coriolis forces, the water's motion would be governed almost entirely by pressure gradients. The flow would be largely radial, moving straight toward the poles rather than spiraling. In the northern hemisphere, the water would rush up the former slopes of the Arctic basin, carving new channels into the permafrost. In the southern hemisphere, the Antarctic plateau would be inundated, its ice sheet melting from below as warm ocean water presses upward. The drainage of equatorial basins would also alter the ocean's depth profile. The average depth would decrease near the equator and increase near the poles, a redistribution that changes the planet's moment of inertia. This shift would cause a subtle wobble in the Earth's axis, a motion that would be recorded as a slow precession over centuries. We don't really know how large that wobble would become because the models assume a rotating planet. Removing that assumption introduces uncertainties that stretch the limits of current simulations. If the megatsunamis are as fast as the calculations suggest, they would outrun any warning system. Coastal cities would have no time to react. The wave would strike before the first siren could sound. The force of impact would be measured in gigapascals, enough to crush steel and pulverize rock. In the wake of the wave, the shoreline would be scoured clean, leaving a jagged scar of basalt and sand. The debris would be thrown back into the ocean, where it would be caught in the swirling currents heading toward the poles. The new polar seas would be cold but not uniformly frozen. The influx of tropical water would keep surface layers above the freezing point, at least during the first decades. Over time, heat exchange with the atmosphere would lower temperatures, and the seas would gradually refreeze. The process would be slow, perhaps taking millennia, but the initial period would be a chaotic mix of liquid and ice, with floating ice flows colliding with each other like broken glass. One small detail that remains clear in the calculations is the formation of a permanent trench along the former equatorial bulge. As the bulge collapses, the sea floor settles into a shallow depression that runs roughly east-west, a relic of the planet's former shape. Even after the water has drained, this trench would persist as a low-lying corridor, a subtle fingerprint of a spin that once was. The moment the planet ceases its spin, the invisible hand that nudges moving air to the right in the north and to the left in the south vanishes. Without that steady push, the familiar jet streams lose their backbone. They were thin, fast ribbons hugging the tropopause, their speed fed by the balance between pressure gradients and the Coriolis tilt. In the new stillness, those ribbons flatten, spread, and crumble into a chaotic sea of slower, broader currents. I find it hard to picture a jet stream suddenly turning into a sluggish river of air, but the physics forces the picture. Pressure differences that once rose gently from equator to pole now spike dramatically. The sun-lit side of the planet basks in relentless heat. The opposite side freezes under an unending night. The temperature gap can reach several hundred degrees Celsius across a few thousand kilometers. Air on the hot side expands, rises, and rushes toward the cold side, where it collapses and sinks. The resulting pressure gradient is immense, and the atmosphere answers with wind speeds that dwarf anything we have measured today. In some models, gusts break the sound barrier, roaring across continents like a sudden, invisible wall. Those supersonic gusts would not be smooth. The air would become a turbulent foam, each eddy snapping against the next. The friction at the surface would heat the lower atmosphere, creating a thin, hot layer that further destabilizes the flow. I don't really know how the sound of such a wind would feel, but I imagine a constant, low-frequency hum that vibrates the ground. The gusts would not respect current climate zones. They would slice through deserts, forests, and oceans with equal ferocity, dragging heat and moisture wherever they go. Moisture, once guided into familiar storm tracks by the jet streams, now gathers in massive, vertically oriented columns. Without the Coriolis spin, storms lose their familiar spiral shape. Instead, they become towering, almost spherical convective towers that grow until the surrounding air can no longer contain them. The updrafts inside these towers can reach speeds comparable to the surrounding winds, making the whole system hyper-intense. Rain would fall in sudden, localized downpours that could drown a valley in minutes, then cease entirely for weeks as the atmosphere readjusts. The redistribution of heat becomes a frantic, uneven process. On the day side, the sun pumps energy into the surface, but the air can only carry it away by moving toward the night side. The supersonic winds act like a conveyor belt, yet they are uneven, creating pockets of scorching heat that linger for hours. On the night side, cold air pools in low-lying basins, forming permanent frost fields. The boundary between the two extremes is not a smooth front. It is a jagged, ever-shifting line where hot gusts slam into frigid air, producing shock-like pressure waves that reverberate through the atmosphere. Because the Coriolis effect is gone, the usual balance that keeps large-scale weather systems from collapsing is missing. The atmosphere, now free of that stabilizing twist, can reorganize itself into a pattern of alternating bands of rising and sinking air that span the globe. These bands are not permanent. They drift, merge, and split as the planet's surface absorbs or radiates heat. The result is a constantly shifting mosaic of temperature and pressure that defies any simple classification. We would no longer speak of tropical or polar climates. We would speak of wind-driven hot zones and cold pockets that appear and disappear with the next gust. The oceans would not be immune. Surface currents, previously steered by the jet streams and the Coriolis push, would be ripped from their paths. Wind-driven waves would slam into coastlines from directions that have never been seen before, eroding cliffs that have stood for millennia. The heat carried by the wind would warm the upper layers of the sea on the day side, while the night side would see a rapid cooling that could freeze surface water in places. The ocean's role as a heat reservoir would be compromised, feeding back into the atmospheric chaos. Even the thin air at high altitudes would feel the change. In the stratosphere, where winds are usually gentle and layered, the loss of Coriolis would allow the pressure-driven currents to rise unchecked. The result could be a series of high-altitude jets that cut across the sky at speeds rivaling those of commercial aircraft, but without the predictable routes we rely on for navigation. Satellites, which already struggle with atmospheric drag, would encounter a far more variable drag profile, altering their orbits in ways we cannot yet calculate. All of this paints a picture of an atmosphere that is no longer a set of slowly evolving patterns but a restless, noisy beast. The usual seasonal rhythms would be replaced by a daily cycle of extreme heat, extreme cold, and the wind that tries to stitch the two together. The notion of weather, as we understand it, would dissolve into a series of abrupt, violent episodes punctuated by brief lulls. I admit that many of these scenarios are built on simplified models. Real-world fluid dynamics at such extremes are notoriously hard to predict. The equations that describe atmospheric motion become chaotic when the stabilizing Coriolis term disappears, and small uncertainties can balloon into completely different outcomes. We don't really know which of these imagined patterns would dominate, or whether new, unforeseen structures would emerge. Yet one detail seems unavoidable: the sound of a wind gust at the equator, scraping against the thin, heated air, would carry a tone unlike any breeze we have ever heard. It would be a reminder that even when the planet's spin stops, the atmosphere refuses to stay still. I record the first consequence as a simple temperature gradient that never shifts. One half of the planet receives unbroken sunlight, the other half sits in permanent night. The line between them, if it still exists, becomes a static border, not a moving sunrise. Continuous solar heating drives the daylight side toward a relentless rise. Surface rocks warm until they radiate heat like blackened metal. Air above them expands, climbs, then stalls because there is no evening to cool it. I find it hard to picture a sky that never darkens, yet the physics says pressure would build, then leak toward the cold side. Eternal night cooling works in the opposite direction. Without any solar input, the night side loses heat to space until the ground freezes solid. The atmosphere there contracts, sinks, and forms a dense, cold layer near the surface. I don't quite understand how quickly the temperature would drop, but the trend is unmistakable. The temperature contrast would be extreme. Daylight regions could climb well above 50 degrees C, perhaps reaching 80 degrees C where the sun is overhead. Night regions might plunge below 80 degrees C, especially at higher latitudes. The difference is more than 100 degrees, a gap that no current climate system can bridge. With such a split, the ocean would respond oddly. Warm water on the sunlit side would evaporate, creating thick, humid layers that drift toward the dark side. As they cross the static border, they would cool rapidly and condense, dumping rain or perhaps snow on the night side. I admit I cannot model the exact precipitation patterns, but the basic cycle seems clear. The permanent daylight eliminates the daily rhythm that drives photosynthesis. Plants on the lit side would receive constant photons, but the heat would soon exceed the tolerance of most enzymes. Leaves would scorch, chlorophyll would degrade, and the net primary production would collapse. On the dark side, photosynthesis is impossible. Only chemosynthetic microbes could survive, if any. Without photosynthesis, the food chain unravels. Herbivores would have no fresh plant material, carnivores would lose their prey. I suspect the only survivors would be organisms that can endure long periods without food, perhaps deep-sea vent species that rely on chemical energy. This is a speculation I cannot verify with current data. Human adaptation becomes a question of shelter and resource transport. In the sunlit zone, people would need cooling systems that can handle continuous heat loads. Air conditioners would run non-stop, drawing power from generators that must cope with a constant demand. In the dark zone, heating would be a constant priority. Insulation would be as vital as oxygen. The border itself would be a place of intense turbulence. Warm air rushing from the bright side would clash with cold air from the dark side, forming a permanent storm front. Wind speeds could reach hurricane levels, and the pressure gradient would stay fixed. I can imagine standing at the edge and feeling a constant, howling gust that never eases. Electricity generation would also be uneven. Solar panels on the lit side would operate at peak output, but they would degrade quickly under extreme heat. Wind turbines on the night side would be useless without wind, unless the border storms provide enough kinetic energy. The mismatch would force massive power grid re-engineering. Water availability would be another challenge. On the bright side, evaporation would outpace rainfall, leading to drought-like conditions despite the presence of clouds near the border. On the dark side, precipitation might accumulate as ice, creating thick permafrost layers that block groundwater flow. Humans would need to transport water across the static line, a task made hazardous by the constant storms. The atmosphere itself might rearrange over long periods. Continuous heating could cause the lit side's air to rise high enough to escape the planet's gravity in small amounts, while the dark side's cold air sinks and densifies. This slow loss of gases could thin the overall envelope, but the timescale is uncertain. I don't have a precise figure, only a qualitative sense that the balance would shift. Biological clocks would break. Organisms that rely on day-night cycles for hormone regulation would lose their cues. Humans, too, would experience sleep disorders, as the absence of darkness removes the natural trigger for melatonin. Artificial lighting schedules could be imposed, but the psychological strain would be severe. I can't say how long societies could endure such stress. Geologically, the lack of rotational forces would alter the shape of the planet. The equatorial bulge, maintained by spin, would relax, making the Earth more spherical. This would shift the distribution of sea level, possibly flooding low-lying areas on both sides. The change would be slow, but it adds another layer of complexity to the scenario. In the end, the picture is one of two worlds glued together. One burns, the other freezes. Both are hostile to life as we know it. The static line between them is a permanent storm, a razor-thin zone where heat and cold meet and never settle. I notice that at the very edge, ice crystals cling to the wind-blown dust, catching the faint starlight that reaches even the dark side. The liquid iron that swirls deep beneath our feet owes its motion to the planet's spin. When that spin stalls, the Coriolis forces that keep the flow organized begin to wane. I find it hard to picture a core suddenly losing its guiding hand, but the physics forces us to imagine a sluggish churn. In a rotating Earth, the outer core behaves like a giant electric generator. The motion of conductive fluid through existing magnetic lines induces a field that, in turn, sustains the flow, a feedback loop called the geodynamo. Stop the rotation, and the loop loses its rhythm. The dynamo slows, and the field weakens. Measurements of Earth's magnetic intensity already show a slow drift. A sudden halt would accelerate that drift into a rapid decay. The dipole strength could drop by orders of magnitude within a few days, perhaps even hours, depending on how abruptly the angular momentum disappears. A weaker field means the magnetosphere, a bubble of magnetic pressure, shrinks. The bow shock that deflects charged particles from the sun would retreat closer to the surface. I don't really know how the shape would settle. The equations become tangled when the driving rotation term vanishes. Cosmic radiation, which the field normally repels, would find new pathways. High-energy protons and heavy ions would penetrate deeper into the atmosphere, raising ionization rates at lower altitudes. The increase would be most noticeable at latitudes that previously enjoyed strong protection. Radiation dose at the surface would climb modestly, but for aircraft cruising at 10 kilometers, the change could be stark. Pilots and passengers would be exposed to fluxes comparable to those encountered on a polar flight today, only now the exposure would be global. That shift would force a rethink of flight routes and shielding standards. The auroral ovals, those shimmering curtains near the poles, would no longer be confined to high latitudes. As the magnetic field weakens, the regions where solar particles spiral along field lines would spread toward the equator. Night skies over tropical cities might acquire a faint, persistent glow, a reminder that the shield is receding. Such an expansion would not be merely visual. The same currents that light the aurora also drive geomagnetic storms. With the field diluted, the coupling between solar wind and ionosphere would become more efficient, allowing storms to dump larger amounts of energy into the upper atmosphere. The result: more frequent, more intense fluctuations in the magnetic field measured at the ground. Power grids, already vulnerable to geomagnetic-induced currents, would feel the strain. The slower the field, the larger the area over which a storm's electric field can drive currents through long conductors. Transformers could experience saturation far from the traditional storm-prone zones, leading to unexpected outages. Engineers would have to redesign protection schemes for a planet that no longer hides its poles. Satellites orbiting in low Earth orbit would lose a key layer of protection. The Van Allen belts, held in place by the magnetic field, would collapse, allowing high-energy particles to bombard spacecraft directly. Battery life, sensor noise, and even structural integrity would degrade faster than current designs anticipate. Mission planners would need to factor in a constant background of radiation that today is only a seasonal concern. Communication links that rely on ionospheric reflection would also shift. The ionosphere's density profile is shaped by the balance between solar radiation and magnetic confinement. A weakened field would let more charged particles reach lower altitudes, altering the layers that radio waves bounce off. Some frequencies might become unusable, while others could open up unexpectedly. Navigation systems that depend on magnetic compasses would become unreliable almost instantly. The compass needle aligns with the local field, and if that field is reduced to a fraction of its former strength, the needle would wobble, pointing in erratic directions. Pilots and sailors would have to abandon magnetic headings for inertial or celestial references. Biological systems that have evolved under a steady magnetic background might feel subtle stress. Certain migratory animals use geomagnetic cues to navigate. If the field's intensity drops, those cues could become ambiguous, leading to disorientation. Researchers would be left scrambling to determine whether observed changes in migration patterns stem from the field loss or from other environmental factors. Even the planet's atmosphere would feel a gentle tug. Charged particles that once spiraled harmlessly around field lines would now strike atmospheric molecules more directly, producing additional ionization. This could affect the formation of noctilucent clouds, those thin, high-altitude veils that appear at twilight. Their prevalence might rise, giving the night sky a slightly hazier sheen. All of these effects hinge on a single premise. The magnetic field is tied to rotation. If the Earth's spin were to cease, the dynamo would not simply pause. It would lose the organizing force that keeps the flow coherent. The resulting field would be patchy, fluctuating, and overall much weaker. We don't really know how quickly the field would collapse. Numerical models suggest a rapid decay, but they rely on assumptions about core viscosity and heat flow that remain uncertain. Laboratory experiments with liquid metal can mimic some aspects, yet scaling those results to planetary dimensions is a stretch. What is clear, however, is that the magnetosphere would cease to be the robust shield we take for granted. Its disappearance would expose the planet to a steady drizzle of particles that today only manage a brief tap during storms. The consequences would ripple through technology, biology, and the very appearance of the night sky. One quiet observation that might linger after the upheaval. A lone weather station near the equator, designed to measure wind speed, would record an unexpected, faint auroral hiss in its radio spectrum, a soft hiss that never belonged there before. The planet's shape is not a perfect sphere. It is flattened at the poles, bulging at the equator because of rotation. If that spin were to stop abruptly, the centrifugal push that holds the equatorial rim outward would vanish in an instant. The solid interior would begin to feel a new balance of forces, and the bulge would start to shrink. Without the outward fling, the equatorial region would relax inward by a few hundred meters. That may sound modest, but the mass that moves is enormous. The mantle, already plastic over geological time, would flow slowly toward the mid-latitudes, while the crust would be forced to accommodate the new geometry. A direct consequence of the bulge's reduction is a redistribution of the oceans. Water that once sat higher at the equator would drift toward the poles, raising sea level there by several hundred meters. Low-lying coastal basins near the former equator would dry out, while previously ice-capped regions would become inundated. The change would not be uniform. Basins with deeper crustal roots would hold more water, creating a patchwork of new shorelines. The crust itself would not settle quietly. As the equatorial compression eases, tensile stresses would appear in the mid-latitude belt, while compressive stresses would concentrate near the former bulge. Those stress patterns would drive faulting on a scale far larger than any modern earthquake sequence. Existing faults would be reactivated, and new fractures could cut across continents that have been stable for millions of years. I find it hard to picture a continent cracking open under such a global reload, yet the physics does not forbid it. When stresses exceed the strength of brittle rock, slip occurs, and the sudden release would generate seismic waves that travel the entire planet. The frequency of such events would rise dramatically, perhaps producing a background tremor that never fully ceases. If the crust is being ripped and squeezed, magma pathways are likely to be altered as well. The mantle's convective cells would be nudged by the shifting surface load, opening fresh conduits toward the surface. That could spark a surge in volcanic eruptions, especially in regions where the lithosphere is already thin. Basaltic flows might spread across former plains, while explosive eruptions could blanket mountain valleys with ash. Long after the initial adjustment, the planet would continue to seek a new equilibrium. The mantle, still viscous, would slowly redistribute mass to support the more spherical shape. This tectonic re-equilibration would take millions of years, during which mountain ranges might be uplifted or eroded at altered rates. The overall pattern of plate motion could shift, changing the direction of subduction zones and the growth of new crust at divergent boundaries. Because the mantle flow is tied to surface topography, the altered load could modify the direction of convection rolls. A subtle change in roll orientation would, in turn, affect the long-term drift of plates. That feedback loop is difficult to model. We do not really know how quickly the mantle would respond to a sudden, planet-wide load change. One concrete effect that can be measured, even in a thought experiment, is the change in crustal thickness beneath the equator. Current seismic surveys show an average thickness of about 35 km there. After the bulge collapses, the crust would be compressed, potentially thinning by a few hundred meters. That thinning would be detectable as a slight increase in gravity anomalies over the former bulge. The whole process would unfold over a hierarchy of timescales. Seconds for the initial loss of centrifugal force, hours to days for the most violent seismic bursts, centuries for the first major sea level adjustments, and millions of years for the final tectonic balance. Each stage would leave its own imprint in the rock record. We don't really know how the interplay of stress, melt, and mantle flow would resolve in detail. The models we have assume gradual changes. A sudden stop pushes every parameter beyond its usual range. Still, the physics points to a planet that would gradually reshape itself, shedding the equatorial puff and settling into a smoother, more spherical form. A final note. If you were to stand at the equator a few months after the spin stopped, the horizon would appear a little lower, as the ground beneath you sank by a few hundred meters, while the distant pole would loom higher, its coastline pushed inland by the same amount. The moment the planet's spin vanished, the first thing living things would feel is a sudden loss of day-night rhythm. Light would linger at the equator, darkness at the poles, and the sky would never change for most places. Without the Coriolis push that now steers winds, atmospheric cells would stall, and the familiar breezes would grind to a halt. I find it hard to picture a world where the air simply sits, waiting for a force that no longer exists. Temperatures would begin to stratify, a permanent furnace at the sub-solar point, a permanent freezer on the opposite side. That binary would rip through habitats, forcing species to choose between scorching sand and frozen stone. Most terrestrial animals rely on seasonal cues to time reproduction. Those cues would disappear and breeding cycles would collapse. Insects that emerge with the first warm sunrise would never know when to hatch. Plants, too, would be stranded. Photoperiod governs leaf growth, flower opening, and seed set. With one half of the globe locked in perpetual night, photosynthesis would cease there, starving the food web that depends on it. The immediate consequence would be a wave of mortality across the lower trophic levels. Small mammals, birds, and reptiles would find their insects gone, and the cascade would rise upward. That is the first thread of a mass extinction risk that could sweep the planet. Marine life would not be spared. The ocean's surface would develop a permanent day side, where heat drives evaporation, and a night side, where cold traps water vapor. This imbalance would set up a single, massive gyre that pushes surface water toward the night side, leaving the day side starved of nutrients. Upwelling zones, the lifeblood of plankton blooms, would shut down. Phytoplankton would wither, and the entire marine food chain would falter. I don't really know how long a few weeks of no plankton would take to translate into a collapse of fish stocks, but the direction is clear. Coastal ecosystems, already fragile, would face an added blow. Without the regular mixing of waters, oxygen levels would drop, creating dead zones that spread like ink across the shallow shelves. Those zones would swallow mussels, crabs, and the juvenile fish that depend on them. Terrestrial migrations would become frantic. Species that once moved only a few kilometers each season would be forced to travel thousands, seeking the narrow band where temperature and light are tolerable. Large herbivores, such as ungulates, would chase the shrinking savanna that follows the moving twilight line. Predators would trail behind, their success rates dropping as prey becomes scattered and exhausted. Birds that navigate by the sun would lose their compass, and many would crash into the night side, unable to reorient. Some might adapt, using magnetic cues, but the magnetic field itself would be altered by the halted rotation, adding another layer of confusion. Human societies would feel the strain almost immediately. Agriculture, the backbone of food security, depends on predictable seasons and regular sunlight. Crops planted on the night side would never see a sunrise, while those on the day side would scorch before they could mature. Farmers would scramble to relocate fields to the thin twilight belt that circles the planet, but that belt is narrow, perhaps a few hundred kilometers wide. Land there is already contested, and the sudden demand would spark conflicts over every hectare. Even in the twilight zone, water availability would be erratic. The permanent heat on one side would drive massive evaporation, feeding storms that never reach the night side. Irrigation would become a gamble, with canals drying up or flooding without warning. Livestock would suffer the same fate as wild grazers. Heat stress would reduce fertility, and cold stress would increase mortality. The loss of animal protein would push human diets toward whatever could be cultivated in the narrow band, narrowing nutritional diversity. Infrastructure, designed for a rotating world, would begin to fail. Power grids rely on predictable demand cycles. With constant daylight or darkness, consumption patterns would shift dramatically, overloading some lines and leaving others idle. Buildings constructed to withstand daily temperature swings would crack under a constant extreme. Roads, laid on ground that once expanded and contracted each day, would buckle as the crust settled into a new, unchanging stress pattern. Water treatment plants, calibrated for regular flow, would be overwhelmed by the surge of meltwater from the night side's frozen reservoirs. Floods would carve new channels, undermining bridges and contaminating supplies. Transportation networks would be crippled. Ships that once rode predictable currents would find themselves stranded in stagnant seas, their engines straining against a water column that no longer moves. Air travel would be hampered by the loss of jet streams that once guided efficient routes. Medical services, already stretched, would confront new disease vectors. Insects that thrive in the warm, stagnant air of the day side could spread pathogens unchecked, while the night side would see a rise in cold, adapted microbes. Communications satellites, launched into orbits that depend on Earth's rotation for stability, would drift into erratic paths, jeopardizing the global flow of information. Without reliable data, coordination of relief efforts would falter. The combined pressure on food, water, shelter, and health would test the resilience of human civilization. Some communities might survive by reverting to low-tech, self-sufficient practices, but the majority would face shortages that could spiral into famine. We don't really know how quickly societies would fragment, but history shows that scarcity breeds competition. Borders that once seemed stable could dissolve, replaced by ad hoc zones of control around the few viable farms. Science would scramble to engineer solutions. Greenhouses that mimic day-night cycles could buy time for crops, yet they require energy that is itself scarce. Genetic modification might produce plants tolerant of constant light or darkness, but the rollout would be too slow for immediate need. In the oceans, aquaculture could replace wild catches, but the same nutrient starvation that plagues plankton would limit growth of farmed fish. Engineers might try to pump nutrient-rich water from the night side, but the energy cost would be prohibitive. Even if technology could patch some gaps, the sheer scale of ecological disruption would leave gaps no machine can fill. The loss of pollinators, for example, would cripple any attempt to grow fruit in the twilight belt, regardless of greenhouse conditions. Animals that managed to survive would become the new keystone species, their behaviors reshaping the remaining ecosystems. A few hardy rodents might dominate the night side, their burrows altering soil composition and creating micro-habitats for insects. On the day side, heat-adapted microbes could form mats that trap carbon, but they would also excrete acids that further degrade soil. The feedback loops would be subtle at first, then accelerate as conditions harden. Human cultures would adapt their calendars if they still needed them to the new reality. Festivals tied to solstices would lose meaning when the sun never sets or never rises for most people. Stories would emerge about the old sky, a nostalgic recollection of sunrise and sunset that now feels as distant as a myth. Those stories would help some cope, but they would also remind us of how fragile the old balance was. In the end, the planet would settle into a new equilibrium, one defined by a permanent gradient of heat and cold, a thin habitable ring, and a patchwork of surviving life forms. The details of that equilibrium are still speculative, and our models can only approximate what might happen. I find it hard to picture the exact shape of the new coastlines after the oceans redistribute themselves, but satellite images would soon show a stark line where water once lapped gently against sand. That line, illuminated by the unending sun, would be the first visible marker of a world that has stopped turning. The Earth's path around the sun would not be torn from its track the moment the planet's spin stopped. Its orbital speed, set by the balance between solar gravity and the momentum it carries from its birth, would stay the same. Nothing in the equations of motion for a heliocentric orbit cares whether the planet turns on its axis. What does change, however, is the way the planet's axis behaves in space. Right now, the Earth is a slightly flattened sphere. The bulge at the equator gives the sun and moon a lever to nudge the axis, producing a slow wobble that completes a cycle every 26,000 years. If the spin vanished, that bulge would relax, the shape would become more spherical, and the torque that drives precession would shrink dramatically. I find it hard to picture a planet suddenly losing its centrifugal flattening. The solid interior would slowly readjust, crustal stresses would shift, and the mass distribution would settle into a new equilibrium. That adjustment would damp the precessional torque, perhaps leaving the axis almost fixed relative to the distant stars. A fixed axis has consequences for the Milankovitch cycles that modulate climate over tens of thousands of years. The three classic components, eccentricity, obliquity, and precession, each alter how sunlight is distributed across latitudes and seasons. With precession essentially gone, one of the three rhythmic drivers would be missing, and the remaining two would dominate the long-term insulation pattern. Obliquity, the tilt of the axis, would no longer be forced to swing back and forth by the same precessional torque. In the absence of that torque, the tilt could become more stable, or it could wander under the influence of other, weaker forces. Some models suggest that without the spin-induced bulge, the tilt might drift toward the value that minimizes solar torque, Perhaps a few degrees, perhaps more. We don't really know how the planet's mantle and core would respond over millennia. Even if the tilt settled, the Earth would still travel along an ellipse that is only modestly altered by planetary perturbations. Its eccentricity would continue to cycle between about 0.003 and 0.05, 8/100,000-year intervals, driven by the gravitational tugs of Jupiter and Saturn. Those cycles are independent of the planet's rotation, so the shape of the orbit would remain as it is now. What about tidal locking? The Sun already raises a tiny tide on the Earth, and the Moon raises a much larger one. Over billions of years, those tides drain rotational energy and can lock a body's spin to its orbit, as we see with the Moon itself. If the Earth's spin were removed instantly, the immediate tidal torque would be negligible, but the long-term evolution would be altered. Without a rapid spin, the planet would present a constant face to the Sun much sooner than it would have otherwise. The timescale for a full tidal lock to the Sun is still on the order of tens of billions of years, far beyond the Sun's remaining life. Yet the cessation of spin would shorten that interval dramatically, because the angular momentum that must be shed is essentially zero. In that scenario, the Earth would gradually settle into a configuration where one hemisphere forever faces the Sun, while the opposite side stays in perpetual darkness. Such a configuration would rewrite the climate's long-term rhythm. The hemisphere locked to the Sun would receive continuous heating. The night side would radiate heat into space, cooling to a deep freeze. Heat transport by oceans and atmosphere would try to smooth the contrast, but the fundamental driver, steady insulation on one side, would dominate. Seasonal swings driven by the Earth's orbit would still occur, but they would be expressed as subtle shifts in the angle of the Sun's rays rather than day-night cycles. Because the orbital speed is unchanged, a year would still last about 365 days of the planet's former rotation. The Sun would appear to crawl slowly across the sky of the Sun-facing side, completing a full circuit once per orbit. On the dark side, the Sun would never rise, and the sky would be a permanent black dome punctuated only by distant stars. If the axis remained tilted, the Sun-facing hemisphere would experience a gradual shift in solar altitude over the year, producing a kind of season that is purely geometric. The magnitude of that shift would be set by the product of the tilt and the orbital eccentricity. With precession gone, the timing of the maximum solar height would be locked to the point in the orbit where the planet is closest to the Sun, rather than drifting over millennia. The Milankovitch cycles that rely on precession would therefore disappear from the climate record. Ice Age timing, which in the real world is linked to the alignment of perihelion with summer in the northern hemisphere, would lose that synchrony. The climate system might still respond to eccentricity and tilt, but the pacing would be different, perhaps more regular. One might wonder whether the loss of precession could stabilize the climate enough to avoid the most extreme glaciations. The answer is not obvious. The removal of a forcing term could reduce the amplitude of temperature swings, but the permanent day-night dichotomy would introduce a new, far larger gradient. The net effect could be a planet that oscillates between a scorching day side and a frozen night side, with a narrow belt of temperate conditions circling the terminator. The terminator, where the Sun hovers at the horizon, would become the most hospitable strip. Its width would depend on atmospheric heat transport efficiency, which itself would be altered by the loss of Coriolis forces that arise from rotation. Without Coriolis, wind patterns would be more directly driven by pressure differences between the hot and cold sides, perhaps forming a single, planet-spanning circulation cell. Even the magnetic field, which is generated by the rotating liquid outer core, would likely collapse without spin. A weakened or absent magnetosphere would expose the atmosphere to solar wind stripping, gradually thinning it over eons. That loss would further affect heat retention and could shift the balance of the day-side and night-side temperatures. All these effects intertwine, but the core orbital picture stays simple. The Earth would keep moving around the Sun at the same speed, its elliptical path unchanged, while the axis would lose the precessional wobble that currently mixes the timing of seasons. The long-term climate cycles that depend on that wobble would fade, leaving only the slower eccentricity and tilt variations to modulate the sunlight that reaches the planet. If we stare at the night sky from the Terminator, we would see the Sun forever perched at the edge of the horizon, a thin disk that never dips below. The stars would rotate around us once per year, tracing slow arcs that mark the passage of time in a way that feels both familiar and alien.